Okay, hello. I've been trying to put together a PowerPoint. I've, of course, used the one that your book does have, but I've added a few things to it. I'm going to try to divide this PowerPoint probably over several different video sessions. So I'll go ahead and start. We're going to go through the first few pages of your book, and then I'll end it and post it, and then I'll start another one here shortly. So let's go ahead and start. We're in chapter 40 of your book, going over fluids and electrolytes. And it is very important to have a good understanding of fluids and electrolytes in order for you to just basically understand all of the different body systems. So let me go ahead and share my screen. Actually, I don't think I did it right. Me and technology, let's see here. Okay, there we go. Okay. Okay, we're about ready to start here. Okay, we're ready. So we're going over chapter 40, fluids, electrolytes, and acid-base balances. Now, we're not going to touch on acid-base balance until a video I'll probably post tomorrow. So make sure when you start reading your chapter that you do read the objectives, okay? And that you have an idea of what you're studying. And also, if I were you, I would probably go to your book resources under course point and find the key point page. That should be under your student resources. Also read through that. I would read through that before I begin my reading of the text. And that should give you kind of a better idea of what you should be looking for as you read. So we're going to talk briefly about the functions of water in the body. It's very, very important for us to have water. You know that we're supposed to be drinking good amounts of water every day. At least, I can't remember exactly the total, but like 8 to 10 bottles of water, which probably would be like those, at least I'd say the 10 to 12 ounce size bottles, and at least probably 10 of those per day in order to be good, really nice and healthy. Again, I'm not the very best at that by any means. I do know it even helps when you are trying to lose weight, that you have a really, really good intake of water. It's important because of what water does within the body. So let's look at this very quickly. It does transport nutrients to cells and waste products from cells. So getting nutrients and food to our cells and getting the waste products that are then created out of the cells. Also, we're transporting hormones and enzymes, blood platelets, and red and white blood cells throughout the body. Those, of course, those blood cells are important. White blood cells are important because of fighting infection, keeping us safe, protecting the body. Red blood cells, of course, are very important in carrying oxygen to the cells and taking that CO2 away from the cells. Platelets are important if we ever need the blood to clot for whatever reason. If there's an injury to the tissue and bleeding occurs, platelets are just one of the important factors in stopping the bleeding. Also, fluids will facilitate cellular metabolism and proper cellular chemical functioning. That's what we'll be kind of going into more detail. It acts as a solvent for electrolytes and non-electrolytes. Helps maintain normal body temperature, facilitates digestion and promotes elimination. If we're not, if our patient is not drinking enough fluid, then there is a risk, even in that situation, of the patient possibly becoming constipated, because we do need good fluid intake to promote good digestion and elimination. And it acts as a tissue lubricant. Okay. There we go. So extracellular, so there's different types of fluid within the body. I should say it more like, where is the fluid actually? Where is it being compartmentalized? Where is it being held? So within the cells, there's about 70% of our fluid. So really most of our fluid is actually inside of our cells. What we kind of tend to look at more is the extracellular fluid, the fluid that is outside of the cells. That's going to include both your intravascular fluid and then your interstitial fluid. Intravascular is just what it says, the fluid that is within the vascular system, but not including the actual cells. The fluid itself, of course, within the cell is intracellular. The fluid that is around the cells, that is extracellular. When it's around, the fluid that's around the cells within the vascular system, so meaning within all the blood vessels, with all the arteries and veins and capillaries, that is intravascular fluid. Interstitial fluid is the fluid that is actually pushed out into the tissue. And there has to be a constant exchange of all of that fluid in order to maintain homeostasis, okay? So let's continue. So a healthy person, the total body weight is between 50 to 60%, fluid is up to 50 to 60% of the body weight. Now, an infant has considerably more fluid, body fluid, and extracellular fluid than does the adult. And they are more prone to fluid volume deficits. Also, gender and amount of fat cells affect the body. Women and obese people have less body water because fat, just like it says, fat contains less body water. So that is why overall then obese people have less body water. And women typically have a little bit less than men because overall there is more body fat on a female versus a male. Males tend to have more muscle. Okay, just the way we're made. Okay, so that is just showing you that in a preterm baby, that almost 80% of the composition of the body of the baby, the preterm baby, is water. For the neonate, so like a newborn, it's about 70%. And there's basically, as you age, you are less and less made, I guess you could say, of fluid, less body fluid per based upon weight. So an older adult, a female is a little bit less even than a male in comparing the two. Okay, so again, here that means that really hydration then is very important for different reasons for your very young and your very old. Okay. Oh, I'm just trying to go to the next slide. This is a different picture, and it is showing you again kind of just where the fluid is within the body. So again, total body fluid is 50 to 60% of your body weight. And of that fluid, a lot of it here it's showing you 35 to 40% is within the cell. I'm sorry, 35 to 40% of your body weight is actually cellular fluid. 5% is plasma. 10 to 15% of your body weight is fluid that is within the tissues, the actual tissues. And then extracellular fluid. Well, I'm sorry, both of these are components of extracellular fluid. So the plasma is what is in the vascular system around the cells. The interstitial fluid is the fluid that is pushed into the tissue. Okay, both of those comprise extracellular fluid. And then this B over here, this is just again showing you if the fluid inside the cell is called intracellular. If it's around the cell, it's called extracellular. Here again, it is showing you that the cells, the fluid that is around the cells, but within the vessels, that is intravascular fluid. And then the fluid that is in the tissue space, but not inside the cell, that is the interstitial fluid. Both of those being extracellular fluid, okay? So just remember, when you are measuring serum electrolytes, you're not measuring the electrolytes within the serum, I'm sorry, you are measuring it within the serum or plasma, not inside the cell. The serum is around the cells. So intracellular fluid is inside the cells. And it's going to have a different electrolyte composition, the fluid that's inside the cell versus the fluid that is outside of the cell. When we're measuring labs and getting those lab results, say for instance sodium, serum sodium level is normally 135 to 145. That is a sodium level that is around the cell, not inside the cell. If we had a tiny, tiny syringe and could measure inside the cell, it's very opposite. We'll talk more about that in a minute. If you were looking at sodium, sodium is very low normally inside the cell. It is the high on the outside, 135 to 145. Potassium is the opposite. Potassium is relatively low if you're looking at the serum, which is around extracellular. It's a 3.5 to 5.0. But if you had a tiny syringe and could measure the potassium level inside the cell, then it is very high. Okay, it's just, so again, the way that the body works and the balance of electrolytes. More potassium is on inside of cells and less is on the outside. Sodium is the opposite. More of your salt, your sodium, is on the outside of the cell, not on the inside. Okay. Okay, and make sure you understand that the fluid, that the extracellular fluid pushed into the tissue is interstitial fluid. And then that extracellular fluid that's found around the cells, but within the vascular system, that is the intravascular fluid. Okay, let's go on. So just a quick note here, some people forget this, but what is the difference between serum and plasma? So both are the extracellular fluid found within the intravascular space, the space of your vessels. And but serum is basically the plasma minus the clotting factors. Okay, so plasma includes your clotting factors. Serum does not include the clotting factors. And probably not just the clotting factors. Also remember, just if you've heard it, but we know that in our ongoing fight against COVID, that one of the things that is a therapeutic agent is the convalescent plasma. That is the plasma that comes from a person who did have COVID recently and was able to fight it off and become healthy again. But they take the serum, so they're taking this product, intravascular fluid. It's within the vascular system, but it's not the actual cells, it's around the cells. They're taking that serum and it contains, it does not, they're taking the plasma. And so the plasma will of course have the clotting factors, but it also has the other factors of the antibodies. And they're giving that plasma, convalescent plasma, to patients to help them fight off the COVID-19 if they have an active case. Okay, so just very quickly, we'll get back to some of that in just a minute. The cations, now those are the electrolytes within the cells, both inside the cells and outside the cells, but within the fluid of the body. Cations are positively charged elements, I guess you could say, and ions are negatively charged ions. And then it's very important for homeostasis, and that's just that natural balance of the body, that your total cations are equal to your total anions. And the concentration of your electrolytes, when we're looking at, say, a serum sodium level or a serum potassium level, is normally measured in milliequivalents per liter. Okay, and normally when you even administer, say, potassium, it's not in milligrams, it is in milliequivalents. So kind of keep that in mind as we go through pharmacology. Solvents are liquids that hold a substance in a solution, And then solutes are the substances dissolved into the solution, the electrolytes and non-electrolytes. So again, that is just one of the reasons that fluid balance is very important and having enough fluid, because water actually, that is the actual substance that is holding our electrolytes. And of course, those electrolytes, two of the main ones, well, they're all important, but sodium and potassium. And to help have the correct balance, you have to have enough fluid, okay? Can't have too much, can't have too little. So, well, again, we'll probably go into this more here on the next presentation that I do, but what do these different electrolytes do in the body? So sodium is very important. It controls and regulates the volume of fluid, of body fluids. Remember I said that water follows salt. So if we end up getting rid of excessive amounts of sodium for whatever reason, then we're going to probably also be getting rid of extra water, and probably the patient would become dehydrated. If we're retaining water, then if we're keeping sodium, sodium is going to then help. That's going to cause a retention of fluid, and we're going to end up having too much water and salt within the body. Potassium is a very important chief regulator of enzyme activity. Very important also in the regulation or of the heartbeat, okay, and the muscle contraction related to the electrical activity of the heart. Potassium is very, very important there. So again, when my potassium is either low or high, the first thing I kind of worry about is what's going on within the heart and what kind of electrical activity is the heart doing. Is it showing signs that the potassium is either too high or too low? Calcium is very important for nerve impulses, also for blood clotting and muscle contraction. We kind of saw that when we were looking a little bit at the heart, and we were looking at how calcium enters the cells that are the contractility cells of the heart. And that's true with muscles in general. Also, calcium is important in B12 absorption. Magnesium is important for the metabolism of carbohydrates and proteins, vital in also actions involving enzymes. Also, magnesium is important in the regulation of the heartbeat and how the heart contracts and everything. Chloride maintains osmotic pressure in the blood. It helps, also produces hydrochloric acid. We'll talk more about that probably in the next video. Bicarb is the body's primary buffer system. And this, when we think of buffer system, we're thinking about the acid-base balance. So again, we'll go over that more tomorrow. Phosphate involved in important chemical reactions in the body, cell division and hereditary traits. Phosphate, I always think of ATP, adenosine triphosphate at the cellular level when your body is making ATP. I think if I remember right, it's made by the mitochondria. And the mitochondria of the cells, that's the energy house. That's where energy is made. That energy is kept in that adenosine triphosphate connection, I guess you could say. So that's why it's important in chemical reactions. Okay. So just as we were talking about earlier, let's go back to intracellular fluid, the fluid inside the cell, extracellular fluid outside of the cell. Here we're looking at both intravascular fluid and then interstitial fluid, the fluid that's inside tissue. So in the inside the cell, your prevalent cation is potassium. Outside of the cell, your prevalent cation is sodium. That is why when you, again, do a sodium level, normally it's 135 to 145. But when you do a potassium, it's very low, but 3.5 to 5 is normal. And that's because sodium is your prevalent cation outside of the cell, while potassium is the prevalent cation within the cell. And there's a picture similar to this in your book. Let's see here. Where is it? It's a similar picture on page 1558. Excuse me, sorry. But this is just basically, again, showing you outside of the cell. Remember, plasma is outside of the cell, but within the vascular system. So sodium is very prevalent. Again, 135 to 145 is normal. But my potassium level and my calcium level and my magnesium level are much lower. Calcium is 3.5 to 5. If I were able to, again, take that little bitty syringe and stick a little cell and get the fluid that's out of the inside of that cell, and then I could do a level on it, well, the potassium would be really, really high. It would be, I'm not sure exactly what, but like 100 or so. Sodium would be less because sodium is mainly found outside of the cell. Potassium, again, is found inside the cell. And of course, then you have all of your other elements as well. Whoops, I went too far. No, I'm going the wrong way. I'm so sorry. I'm gonna need the little arrows. Okay, let me go back. 1 second. Okay, so we were here. Okay. So tell whether the following statement is true or false. Molecules in the body's chemical compounds that remain intact are called electrolytes. False rationale. The molecules in the body's chemical compounds that remain intact are called non-electrolytes. Okay. I'm honestly not exactly sure what that means. I'll let you read your book for that. I don't think that's that important of a principle to understand. Okay, so now let's talk about, this is very important to understand. How do fluids move in and out of the body? How do they move in and out of the different compartments inside the cell, outside of the cell? And remember, we mentioned 2 different compartments. We mentioned the intravascular compartment, which is the fluid that is within the vascular system. And of course, we need to maintain that. If we have too much fluid, then we can end up possibly getting high blood pressure and having other problems. If we don't have enough fluid within the intravascular system, then we're going to end up being hypovolemic and having low blood pressure. But also remember, there is a little bit of fluid around the heart within that pericardial sac. There is fluid within our GI tract. Again, fluid is important to help move all of the food and food particles throughout the digestive system. And then as the body is breaking up all of that, then it's keeping everything moving through the digestive system and helping to eliminate the waste products within the GI system. We know that our kidneys are constantly filtering fluids. Okay, so understanding how the different fluids move within the body, it's important. Osmosis. So this is when water passes from an area of a lesser solute or concentration to a greater concentration until equilibrium is established. Okay, and there's a picture of that, and I'll show you another kind of similar picture. Well, on page 1561 in your book, it talks about, so when you're dealing with, let me see here, you are dealing usually with a membrane, some type of membrane, okay, when you're talking about osmosis. And for whatever reason, your actual little particles can't cross that, but water can. And we always have a tendency to want to make things equal. There's just normally a normal response in the body to want to make things equal. So if we have greater concentration on one side than the other, but we can't actually move the particle through that semipermeable membrane, then water is going to go to the opposite. It's going to go from an area of high concentration of solutes to an area of low concentration of solutes to try to dilute it and then make each side equal. So that's how that is how osmosis works. Now diffusion is when across that membrane the particles can move. So those electrolytes can move, or whatever kind of solute you're talking about. So it's going to have a tendency to always just go downhill. Active transport is when you actually need to have energy. So you're going to have to actually burn calories and use energy to move substances through the cellular membrane from the lesser solute concentration to the higher. So again, remember, normally we always want to go kind of like gravity does, from high to low. That's a passive process. If we're having to make things go from a point of low concentration to high, that is not passive. The opposite of passive is active. So that would be active transport. So both really osmosis and diffusion are examples of passive transports. Active transport is, of course, an example of active transport, that you're going to have extra energy being burned in order for that to occur. Capillary filtration is the passage of fluid through a permeable membrane from the area of high to low pressure. Now, all of these, you're going to see examples of these everywhere throughout the body. So let me see if we can go ahead and show you a couple. Okay, so what is an example of diffusion in the body? A very good example of diffusion is within the lungs, especially within that alveoli, with gas exchange. So we know that within the alveoli, we're taking in a good breath of air, and one of the things that's in that air is oxygen. And so we know that our body initially takes that oxygen. We need oxygen in order to live. For all of our body processes, our tissues need oxygen. So that oxygen is carried through the blood on the red blood cell, goes through the body. Our body then picks up that oxygen, uses it, then puts the waste product back into those red blood cells, and then CO2 is carried. That ends up traveling back to the heart, back to that right atrium, and then right atrium, right ventricle, and then it goes where? To the lungs. Then that travels through the lungs into those, and then you have those little capillaries that are all around those little alveoli. So this picture here is showing you, where's my little thing? This picture here is showing you a little alveoli. Okay, there's the alveoli itself. So this is kind of just showing you the alveoli. You have capillaries that run across the surface, all over the surface of these alveoli. And then you actually have diffusion taking place. There's an area of high concentration of oxygen here and low here. And what's going to happen, we're going to pick up oxygen. And then we have lots of CO2 in our blood. We're going to be putting that CO2 back into the air that's within the lung, that little alveoli. And then we're going to exhale and we're going to breathe out the CO2. So that is an example of diffusion. Oxygen going from a concentration of high in the alveolus to low within the blood. CO2 is really high right now in the blood. It's going to then travel out into the alveolus, and now now our cells are oxygenated, and they're going to go back to the left side of the heart and then out through the body. That is an example of diffusion. Okay, now what about examples of, of osmosis? Okay, this is an important concept to understand when you're thinking about IV fluids. We'll talk more about IV fluids tomorrow, but I do want you to understand these terms: isotonic, hypertonic, and hypotonic. So isotonic, so remember we have an osmolarity within the blood, and we're looking at serum osmolarity. And normally, if we're nice and healthy, then if we needed to get any kind of IV fluids, we normally would want to get an isotonic IV fluid, so that if that fluid is being introduced into the vascular system, that it's not going to really cause any kind of exchange of fluids inside the cellular space and outside of the cellular space. We want there to be kind of the same concentration. So if we're giving any type of fluid that is isotonic, it's an isotonic IV fluid, it's going to have relatively the same concentration of particles in the fluid as are the particles within the plasma. There should be a very similar concentration. Now, there are times when we need to give a hypertonic solution or a hypotonic solution. You have to think about what's going on at the cellular level. And when you're thinking about hypertonic versus hypotonic, this is where it's very important to look at the sodium level. The sodium level, if our sodium levels are off, then we are in a state of being maybe of overall having a hypertonic state within the extracellular fluid. Or if our sodium level is low, then we're having a hypotonic state within the intracellular or extracellular fluid, intravascular. And then that can cause different things to happen to the cells of our body. So let's go. So this picture, and I got this picture from a different website. Let's look first at normal. This is kind of looking at a red blood cell. So if the serum that is surrounding my blood cell is if my sodium level is normal, then that means there's going to be basically then a normal osmolarity. So I would probably have fluid flowing in and out of the cell without any problems, okay? And again, also, if I'm giving an isotonic IV solution, that's not going to really change that movement of fluid one way or the other, okay? It's going to be a nice equal fluid exchange through osmosis. But what if the sodium level around my cells of the body are in a state of being hypertonic? So if I'm giving a hypertonic solution, or if for some reason my sodium level is really high. So if my sodium level is really, really high out around the cell, my cell is going to think, oh goodness, I can't bring sodium in because I can only do osmosis. So some of the fluid that is inside my cell is going to leave my cell to try to dilute the salt that's on the outside. So it's going to cause, to a degree, some of the cells to shrink. What's important here, especially, it can really impact the brain, and it can cause the cells of the brain to kind of shrink. And then that can end up causing mental issues and mental confusion. So when your levels of salt are not where they should be, sodium 135 to 145. If I'm in a state of being hypertonic, and if my sodium level is say 150, then my cells themselves are going to end up becoming dehydrated. Now the opposite is true when you're thinking about a hypotonic solution or a hypotonic environment. So if I don't have a lot of salt over here, so if my salt levels are less than 135 to 145, so say a 125, that's going to cause fluid to go from the extracellular space into the cells, and the cells are going to then swell. And again, that's going to happen in your brain, and that's going to also lead to confusion. It can really, really cause instability and major confusion within your patients. So that's why it's important for that, first of all, for your sodium to be maintained at 135 to 145. And that's also why it's important to give the correct IV fluids. And when we really don't have any other problems going on, then we normally want to try to give an isotonic type solution. The best isotonic solution probably there is 0.9% sodium chloride. We call that normal saline. We'll probably talk more about that tomorrow, but kind of just know that your most common isotonic solution is 0.9% sodium chloride, also known as normal saline. That's not going to really change the environment around the cells. It should maintain an isotonic environment. Okay, so we've talked about different ways that the fluids can move throughout the body. We talked about diffusion. And there, we're not really talking about fluid, but we are talking about oxygen, and we're talking about carbon dioxide. Simple diffusion occurs within the alveoli, and we have that exchange of oxygen and CO2, and that's how we maintain good oxygen levels within the body. Then we talked about diffusion, And that's just the movement of the solutes across the membrane to try to equalize on one side or the other. And then we talked about osmosis, and that's when the solutes themselves cannot move because of that membrane, but the fluid can. And so the fluid is going to, if there's an area of high concentration, fluid's going to go across the membrane to try to dilute this area of high concentration to, again, kind of maintain or achieve equilibrium. Another way is that we move fluids is through what we call hydrostatic pressure and colloid osmotic pressure. And that's how we get fluid into our tissue and then fluid out of the tissue. Here's a good website I found if you want to go there to learn more about it. So when we're talking about these two types of processes, we're mainly thinking about what is going on at the capillary level and how are we getting fluid from the intravascular space pushed out into the tissue. And then how are we getting that fluid back out of the tissue, back into the intravascular space? Both of those things have to occur in order for our tissue to get both nutrients and to get oxygen. So within the capillary system, we have, first of all, fluid is pushed into the tissue due to hydrostatic pressure. And that basically is kind of determined by your blood pressure. Okay, so fluid is pushed from the intravascular space into the tissue. Now, normally we don't push blood cells into the tissue. Those stay within the intravascular space. But we are pushing out fluids and nutrients and oxygen into the tissue. And then you have cellular metabolism occurs. So now you have CO2 and you have waste products, and then the extra fluid, it needs to be pulled back into the capillary system and to return to the heart. That is done by oncotic pressure. So oncotic pressure is made by the presence of protein. Normally we're thinking albumin, and that is a type of protein. That is why having protein in your diet is important. So if your patient has low albumin levels, then some of the fluid and also waste products and everything, those are going to remain in the tissue. So this is one reason that we have swelling. So, but that's not the only reason. There are several reasons that a person may have swelling. It could just be due to increased salt intake. Remember, again, fluid and water follows salt. So sometimes if we have increased salt, we are going to end up with excess water, and some of that fluid will be pushed off into the tissue. Another reason is poor venous return. If it's hard for us to get the blood back to the heart, that can cause, and that probably affects to a degree on not oncotic pressure, but the hydrostatic pressure. But again, heart failure is an example of when you'd have poor venous return and sometimes end up having swelling. Another reason is just too much fluid in general. If we have too much fluid in general, for whatever reason, we've got to put that fluid somewhere. And so sometimes some of that fluid remains in the tissue. And sometimes kidney failure. And again, with kidney failure, you basically are having a problem with fluid balance. And so again, some of that excess fluid can be pushed into the tissue. Okay, let's go on. Okay, this is, again, I took this little slide or picture from that site that I just showed you. It compares hydrostatic pressure and oncotic pressure. So just as I said, hydrostatic pressure refers to the force that is exerted by the fluid inside the blood capillaries against the capillary wall that ends up, sorry, it pushes fluid out of the capillaries into the tissue. And of course, with the fluid also goes oxygen and nutrients. So now that's how the tissue is getting that. And again, that occurs as a result of the pressure of the blood inside the capillaries. So it's definitely tied to blood pressure. This pressure is around 30 millimeters of mercury. So by the time, of course, you know that you normally start out with a pressure of 119 over 79 around in your blood vessels, in the arteries. But then, of course, as those arteries kind of branch downward into arterioles, and then those branch into the capillaries, we keep on losing our pressure. So at this point, the pressure is around 30 millimeters of mercury. And this occurs at the arterial end of your capillaries. It causes filtration. We're filtering and pushing out oxygen and nutrients into the tissue. Now, again, how do we get that out? Let me get a drink real quick. I'm sorry. So we get that out. We get that fluid back out with oncotic pressure. This refers to the force that is exerted by albumin and other proteins in the blood vessels. So normally that protein does not, some of the protein doesn't get pushed into the tissue. It remains in the vessel, albumin. And then that creates a pressure that pulls the fluid, and including the waste products and the CO2, back into the venous side of the capillaries. It occurs due to proteins such as albumin, globulins, and fibrinogens inside the blood capillaries. And at this point, the pressure is around 20 millimeters of mercury, so it's even less. And we call this as a type of colloid pressure. So hydrostatic pressure is a type of fluid pressure, to me, kind of related to blood pressure. The other, on the other side, colloid pressure is a pressure created by those different proteins, such as albumin. This occurs on the venous side of the capillaries. It prevents fluid from leaving blood capillaries. It helps to remove the metabolite waste from the tissues. So this is an example of the capillaries. So here's your capillary. So it, came from your heart, and the blood's pumping through the body. Pressure was 119 over 79. Now it's going through the arterioles. We're losing that pressure. At this point, now the pressure is around 30 millimeters of mercury. Blood is finally traveling through the capillary bed. Now red blood cells, white blood cells, for the most part, they're staying inside the vascular system. But what's being pushed out? Fluid's being pushed out. And along with the fluid, oxygen and nutrients. Now our tissue is using all of that oxygen and nutrients. And now albumin also remains inside those vessels, and it creates a pressure that pulls the fluid back. And along with that fluid now are coming CO2 and the waste products. That's all collecting back into venules, back into veins, back into the vena cava, and back to the heart, the right atrium. So that's kind of how that works. And this is just another picture of showing you oncotic pressure, okay? So I'll let you look at that kind of on your own. But it really is important to understand that oncotic pressure, if you don't have enough albumin, and there is a level, I'll look that up and give it to you, but if you don't have enough albumin, you're going to end up not having good oncotic pressure, and it's going to be more difficult for you to pull fluid back into the body. And you're going to end up possibly, when your patients are really sick because of that, they probably have very low blood pressures because what? We don't have enough fluid within the intravascular space. Yet our patient's very swollen because it's hard to get the fluid back out of the tissue back into the blood vessels. But the blood vessels are actually going without fluid because of that fluid loss. So even though your patient's edematous, they probably would have a low blood pressure. So an understanding oncotic pressure is really, really important. So now we're going back into just thinking kind of in general, where do we get fluids from the body? Of course, we're going to ingest both liquids and foods. We do need to keep in mind that some of our foods, there is fluid within the foods. What we typically try to really measure for sure is the fluid that when we drink or ingest fluids, we try to keep account of that, especially if our patient needs to be on a strict INO, intake and output. And also, just as a byproduct of metabolism, some of the chemical reactions actually create a little bit of water. Okay, and then how do we lose water? Your book goes into more detail, but we lose water through breathing. That's one example of insensible water loss. Just a little bit of moisture that is in our breath as we breathe in and out. Skin perspiration. We always normally perspire a little bit every day. We know that we perspire a lot more when our body is very hot, because that is one way that we can help control our body temperatures through perspiration. And then as we sweat, and then that is evaporated into the air, that helps remove body temperature. Intestinal tract, we do lose some fluid, although it's kind of difficult to measure unless it's very liquidy. We do lose some fluid through our feces. Okay, that is just showing you kind of a typical day of if we ingest, say, 1,300 milliliters of water, and then with our food, we are also ingesting 1,000 mLs. And then we are making maybe even, say, 300 mLs through metabolic oxidation, the chemical processes that are going on within the body. Then our total intake would be around 2,600. Now, when we're looking at output, we're thinking kidneys normally would put out maybe about 1,500 milliliters of fluid. The skin, 600 through sweat, 300 through that insensible water loss through the lungs. The GI tract, 200, for a total of 2,600. Now, keep in mind, it's a little difficult to measure some of those. But we can definitely measure what the kidneys put out. So normally now the kidneys are actually filtering. So in that initial filtration at the very beginning of the nephron, which is the glomerulus, we're actually filtering into that into the glomeruli of the nephrons, a total of 170 liters of plasma. But remember, as the fluid then travels through those nephrons, most of that water, like 90% of it, is being absorbed. We end up excreting only about 1.5 liters of fluid per day, even though we're filtering 170 liters. We're keeping most of it. It's being filtered back into the body by reabsorption throughout the nephron. But we are excreting on average 1.5 liters of urine per day. Also remember that the cardiovascular system pumps and carries nutrients and water in the body. We know that, and we know that lungs regulate oxygen and CO2 levels. What else? Adrenal glands. They're going to help the body conserve sodium, save chloride in water, and excrete potassium. One of the important adrenal cortex hormone that does that is aldosterone. Your pituitary gland stores and releases antidiuretic hormone. We'll try to talk more about that tomorrow. Your thyroid increases the blood flow in the body, increases renal circulation. Your nervous system inhibits and stimulates mechanisms influencing fluid balance. Parathyroid gland regulates the level of calcium in your extracellular fluid. The GI tract absorbs water and nutrients that enter the body through this route. So all the body systems have a role in the homeostasis of fluid and electrolytes. Again, probably if we thought which one is most important, probably we would think kidneys followed by heart. Okay, so let's look at this one. Tell whether the following statement is true or false. A hypertonic solution has a greater osmolarity, causing water to move out of the cells and to be drawn into the intravascular compartment, causing the cell to shrink. Hypertonic solution. Is that true or false? It is true, and we saw a picture of that. Okay, so I'm going to go ahead and stop share. And I'm going to go ahead and end the presentation for now. I'm going to go ahead and save this, and then the next presentation will probably, I'm not sure if we'll start there. We may skip acid-base balance, and I'll make one of those tomorrow. I'm not sure, but we will definitely cover acid-base balance before the day is over tomorrow. I hope you've been doing your reading today. I'm sorry I didn't get these posted earlier. I ended up getting kind of busy today with other things. But thank you for listening. Stay warm. It is Monday night right now, 11:43. So stay warm tomorrow and be safe. And hopefully you can just stay home. We'll see you in here in a little bit.